Okay, I'm back. I've got the equation of motion for this bicycle system written here. And if you recall, on the left-hand side, we have the dynamics of a simple inverted compound pendulum. And on the right-hand side, we have this torque, an effective torque that is governed primarily by our steer inputs for the front and rear. This torque gets higher and stronger the more steer you put in, or the faster you go as U increases. And then you can affect lever arms too, depending on what A and B are, the distance between the wheelbase and that center, and the mass. But this is the equation of motion. What I want to do at this point is take the Laplace transform and write some transfer functions. In particular, I want to know how does steer, both front and rear, affect roll. And writing these as a transfer function gives us an algebraic representation of these different linear differential equations that we have written in the time domain above. So taking the Laplace transform, it's not too hard with this one. We replace the dots with s times the variable, double dots s squared, and that'll basically take care of it. So I can write mh squared s times theta instead of theta double dot minus mgh theta. And these thetas are now a function of, in the Laplace domain, a function of s. And then I've got mb a plus b. I have a delta f dot, so I'll get a s delta f u plus delta f u squared plus a s delta r u minus delta r u squared. Yep. Alright, so now I have an algebraic representation in the Laplace domain where theta, delta f, and delta r are my primary variables here. So the first thing is that once we have this, we can write the characteristic equation of the system. Excuse me, I am in a place with cats, which I'm allergic to, so you're going to get to listen to me sneeze and sniffle occasionally. Apologize about that. Okay, so to write the characteristic equation, we take the left-hand side of the equation, mh squared, and I forgot this was a s squared, it was a double dot, s squared theta minus mgh theta equals 0. Alright, so we have our characteristic equation. This gives us the fundamental dynamics of the system, and we can ask, what is S? Okay, the eigenvalues that govern this particular system. Well, this one's not too hard. It's just a simple quadratic, and we can solve for S. So I can write S squared, first divide through by theta, and then I can write S squared equals mgh over I1 plus mh squared. And then S simply becomes plus or minus the square root of mgh over I1 plus mh squared. Okay, so the numerator is positive mgh. The denominator inside that root is also positive. We have a positive value inside the root. So we end up with a real number. Okay, 2 real eigenvalues. 2 real eigenvalues, but one is positive and one is negative. So we see then, once again, unstable, right? So we have a positive eigenvalue, that's unstable. All right, so that pops up. But we have no oscillations. Okay, real eigenvalues, remember, they just represent either this or this, right? E to the negative st or e to the st. So we have the pendulum basically falls over, unstable or converges. But if a single eigenvalue is positive, the whole system is stable. So that growth to infinity will govern the motion, and we have what we see here on the left-hand side for this system, if there's no torque supplied, so just the fundamental motion. It's going to be useful for us to write S. We can write this in the form of 1 over some time constant tau, right? And I'm going to call, in our case, you can rewrite S as plus or minus, and then 1 over tau 1. We're going to have a few taus here, and I'll show why in a minute. If I write this like that, then tau 1 squared equals I1 plus mh squared over mgh. So I'm going to make that substitution. So we just work with this tau, and we'll bring back in I, mh, g at later points, just to simplify the algebra, and it'll allow us to think about the system in terms of just this time constant representation. All right, so those are the eigenvalues of the system. That's the left-hand side. We got the characteristic equation. Well, how does the right-hand side come into play? Well, we need to write a transfer function like we did for the car. And to do that, we can set delta f and its derivative to 0, and delta r and its derivative to 0, one or the other, and then we can algebraically manipulate the entire equation of motion in the Laplace domain to write two transfer functions, theta over delta f and theta over delta r. And remember, these are functions in the variables in the Laplace domain. So I'll put the s there. So if I find the ratio of these, it gives me a ratio, and this polynomial ratio, that tells me how much roll angle do I get if I plug in some amount of steer. Okay, so this tells us, let's write that. For given steer. So these are going to be useful, and we're going to be able to learn a number of things about them. To do this, right, for example, set delta r dot equal to 0, and then we have the equation. I'm going to bring out theta, and then we have I1 plus mh squared times s squared minus mgh. And then if I get rid of the delta, well, we don't need to set the delta dot because we've already gotten rid of that in the time domain. But I can write the remaining term. So, and I'm going to extract delta f from that too. So delta f mhu a plus b times bs plus u. Right. So notice that, well, delta, I can rearrange this equation to have that ratio that I want. So theta over delta f then equals negative mhu over a plus b times bs plus u all over I1 plus mh squared s squared minus mgh. So we find what we expect. We see that we have the characteristic equation in the denominator, and then we have a polynomial only to s to the 1 in the numerator. And we can use this to think about how the inputs affect the outputs. The inputs being the steer, the output being the roll angle of the bicycle. Alright, so you can similarly write one for the rear steer, but we'll come back to that. I want to move forward and let's just talk about how the front steering affects the roll angle of the bicycle. And then we'll look at later how the rear steering affects it. Right, so I've got this transfer function. The next thing I want to do is just write this transfer function in terms of some time constants. Okay, so I'm going to sort of manipulate the equation here so that we can just write it in a little simpler form that'll be easier to move forward with. So we've already defined this tau 1. So tau 1 squared equals I1 plus mh squared over mgh, and we can manipulate the equation so that we see that in the bottom, the denominator. So I'm going to divide through such that we get that term to show up in the denominator. And if I do that, let's see what I'm doing here. I will Alright, so let's divide the numerator and the denominator by I1 plus mh, by mgh. Right? So divide by mgh. So this is basically multiplying by 1 over mgh and 1 over mgh. So what do we get if we do that? We'll get I1 plus mh squared over mgh s squared minus 1 on the denominator, and then we'll get minus u is the only thing left. The m and the h are going to cancel, and then we'll have a g plus a plus b times bs plus u. Alright, I think that's correct. So delta f equals, let's just rewrite that so we can see it, g a plus b bs plus u, and then I plus mh squared over mgh s squared minus 1. Okay, so we see that we have the tau 1 squared in the numerator now, which is the coefficient to s squared. So I'll be able to replace that. In the top, I want to also have a something times s plus 1 in this parentheses. So if I divide through by, if I pull the u out of the parentheses, I can write u squared over g a plus b b u s plus 1. Alright, and then we've still got this bottom piece. So let's just get all that written. Gh s squared minus 1. Alright, so what I've done here by ensuring that I have these 1 terms in the trailing portion of the polynomial, then we can redefine a few things. So this, the denominator is going to be tau 1 squared. This we're going to call tau 2, right? And then this term, not including the negative sign, we're going to call k, simple multiplier, or a gain. So we can call this k the gain of the transfer function, and then we have the two polynomial chunks written in terms of these time constants. So what does that look like? We have then negative k times tau 2s plus 1 tau 1 squared s squared minus 1. So this exposes sort of the fundamental form of the transfer function. We have the quadratic polynomial on the denominator, the characteristic equation, which we've already found the roots for, or the eigenvalues. And in the numerator, we have some gain k. We've got a negative sign, and then we have tau 2s plus 1, this polynomial in s. Alright, so this is the transfer function in a simplified form, and we can move forward with that. So, what else? Did I want to do anything else in this video? That's it. Alright, so we have our transfer function, and it defines the dynamic system, the relationship between the steer and the roll, and we can think about different steers and how roll is going to be in terms of the Laplace domain. You can convert it back to the time domain and then see the behavior of the roll angle if I give a given steer angle. I guess a couple other, I think that's all I want to go over right now. Right? And we'll come back. So here we go.